Hi everyone, I'm Professor Bergasser, and in this video we're going to be looking at how we apply momentum and energy conservation to processes of collisions. And collisions happen in many different cases. They're anytime you have two or more physical objects that come in contact with each other, that physical contact can be considered a collision. And we're going to use momentum conservation in particular because the forces of interaction in those kind of collisions may be so complicated that they're hard to actually calculate. But if we treat this as a system, the colliding objects as a system, then those internal forces can be hidden away in our total system momentum, and then we just have to worry about what's happening on the outside of our system in terms of the motion of the objects within that system. So let's remind ourselves about our conservation laws. We have a conservation of energy, that's the total mechanical energy, kinetic plus potential. The change of that energy, which is the final minus the initial, is equal to the work done by dissipative forces alone. And again, that's force over displacement, force dot displacement. So if you've got no dissipative forces, friction, viscosity, etc., then the total mechanical energy of the system is conserved. The momentum conservation law comes into play when we're talking about external forces for our system. So again, if we look at the change in momentum, final minus initial, keeping in mind this is a vector quantity, as long as if there's no external forces, or there's no external forces along a given axis, then the momentum is going to be conserved either total or along that axis. Now in the case of collisions, in many cases when we have collisions, they may happen over so short a time span that term, the impulse term, the external force times the chain of time, may become so small that we can effectively neglect it. In that case, we're not worried about the external forces, and so we implicitly have a conservation of momentum expression. So we can make use of those terms, the equivalence of final and initial momentum along each of these axes, to then solve for the motion of our system. In this case, then, all it really matters is what happens with the energy of the system as we go between our initial and final states. So we can organize our types of collisions based on how the kinetic energy of our system changes from the initial to final state. We've got three categories. The first is elastic, and that's the case where the kinetic energy is essentially constant between the initial and final state. We've lost no kinetic energy from the system. We also have inelastic collisions in which there is a reduction in the kinetic energy. And that could be a case where energy is lost through dissipative forces, or it could be stored up in some of our potential energy sources, our conservative force laws. We could also have the case where there's kinetic energy released as a part of a system. We call these superelastic. And most of the cases, these are where we're drawing on some potential energy in the system, and that energy is released as part of the collision and can then add to the kinetic energy of the particles that are participating in that collision. So just as an example of what kind of inelastic collisions we see out in nature, a very common case when we're talking about collisions are automotive collisions. And those are cases where we've definitely lost a lot of energy to the system through dissipative forces. Those forces may be the friction acting between the wheels and the road as things slide to a stop. It's the deformation of the car itself, the energy going into breaking the bonds and bending the metals in the car. Then of course the sound of the collision is going to take energy away from our system. And so in these cases, the change in the kinetic energy of our system, which is also the change in the total energy of the system, is all going away due to the work done by dissipative forces. We can also store some of that energy away in conservative forces, and we see this often when we look at molecular dynamics. And when we have molecules and atoms coming together to form molecular bonds, the initial kinetic energy that's contained in the motion of those molecules may go into storage in the bonds themselves. So in that case, you're losing energy, but it's being stored into these potential energy forms of molecular bonds and could come out at a later point when these bonds break. So the total energy system doesn't decrease, but the kinetic energy does. Now there's a special case of an inelastic collision where the most energy is lost, and that's the case where the collision results in two objects sticking together. And we'll see an example of this later on. But of course, both the examples I show here, a car collision and even two molecules coming together to form a more complex molecule, are examples of perfectly inelastic collisions. And these, as we'll see, are the collisions that give rise to the most energy lost, at least kinetic energy lost, to the system. Now it turns out superelastic collisions happen quite often at the atomic and molecular scale as well. When we look at nuclear physics, the fusion process, where we're taking high energy light nuclei, combining them to form larger nuclei, that releases potential energy in the form of mass energy. And that's Einstein's famous equation, energy equals mc squared. That's the energy that's released by converting some amount of mass into energy. And that energy is then released out into the form of the kinetic energy of the particles that are then produced as a part of this fusion reaction. So here I'm combining a deuterium atom, which is a hydrogen atom with a neutron, and a tritium atom, which is a hydrogen atom with 2 neutrons, and forming helium-4. This is a common reaction when we're studying fusion here on Earth. The energy, the kinetic energy that's released from the mass converted into energy is enough to make those particles coming out much more energetic, and that gives rise to heat, and that's why fusion is seen as an energy source. It's not really creating energy, it's just converting mass into energy, and it does it through these collisions. So we can modify our momentum conservation problem-solving process when we've got these collisions because we're implicitly assuming that momentum is going to be conserved. So as before, we're going to set up our problem, but in particular, we're going to determine what objects in our system are undergoing a collision at any given time, and we'll define those colliders as our system, because that way we can ignore the forces that are acting in between those particles as they come together. So we can write down the expressions for our initial and final momentum along any axis that we're looking, and also the kinetic energies beginning and end. And we should then figure out whether this interaction is elastic, inelastic, or superelastic. In some cases, that might be the thing we're actually trying to find out. So if it's possible, we should determine that. Because we're looking at the case where the collision time is very short, so the external forces don't have time to change the momentum in the system, in collision examples, we can always set the change of momentum equal to 0, so we can set the momentum before and after equal to each other along every axis. And then all we have to do is figure out how we relate the kinetic energies based on whether it's elastic, inelastic, or superelastic. And as before, we'll solve for our unknowns, and then we'll check that our problem makes sense in terms of its units, in terms of our predictions for the problem, and whether it matches some extreme values that we can assume for what the collision is like. So I'm going to go through a series of examples looking at each of these cases of elastic, inelastic, and superelastic collisions to get an idea of how we can solve these more generally. And I'm going to take a very simple case of where we just have two objects, let's say 2 ball bearings that have the same mass, and then we've got one that's moving into the other one, and we want to see what happens as a result of that just classic exchange, classic collision. So again, we're going to set this up by looking at our initial condition, that is the first ball bearing coming in and colliding with the second one, and the event is what happens after that collision. How do they move apart after that collision has occurred, after they've come in contact? So again, we can write down our initial momentum for the system and the final momentum. We're only dealing with a one-dimensional motion, so we just have to write that along one axis. In this case, it's just the mass times the velocities of the particles that are moving. So in the initial case, it's just the first object's initial velocity. And in the second case, it's the masses times the velocities of the 2 objects as they move apart. And we can also write down the kinetic energies. That's just 1/2 mv squared for all the particles that are moving in both cases. Now, for all of our collision examples, we can set the system momentum equal to each other right away, because we're assuming that the collision takes place over so short of time, the external forces don't matter. And for our elastic case, we can set the kinetic energies equal to each other as well. So at this point now, we've got 2 equations. We've got 2 unknowns, the unknown speeds of the particles as they are departing. And at this point, it just becomes algebra, just becomes math. So we can cancel out the things that are common between the equations. We can square the first equation, since in both cases then we have v1 squared on the left side. And when we combine all of these numbers together, what we find is that we have a relationship between the square of the sum of the speeds and the sum of the square of the speeds, the first coming from the momentum equation, the second coming from the kinetic energy equation. And if you expand this out, the only way that this equation can be true is if the combination 2 times the speed of each object has to equal 0. That's the cross term in the left-hand side square. Okay, when you square this right here, you get this cross term out here, and that has to go to 0 for these two things to be equal. Now, how is that possible? Well, it's only possible if one of these speeds is itself 0, one or the other. And you can imagine if the second ball is 0, then it's no way for the first ball to go anywhere because it's blocking the way. So it must be the case that the first ball stops moving, its speed goes to 0, and you end up with the case where you've literally just moved the motion from one object to the other object. This is a classic result of elastic collisions between objects that have the same mass. Now, in an inelastic collision, the setup is exactly the same. We have the momentum before and after, the kinetic energy before and after. The momentum are the same. But in this case, we're losing kinetic energy through this inelastic process. Now, whether that goes to dissipative forces or is stored somewhere is irrelevant. We can still decide that the kinetic energy initially is going to be greater than the kinetic energy afterwards because we've lost energy, kinetic energy in the process. So the math is identical in this case. All right, we have two unknowns. We've got two equations, one of which is a limit. And so we can again do the same math and come up with an inequality between the sum of the speeds squared and the sum of the squared speeds. And that allows us to then see that there's a relationship between the two speeds where those numbers multiplied together have to give us a number that's greater than 0. And really what that's telling us is that's telling us that the two objects have to be moving together in the same direction as a result of this collision. And again, if we look at our momentum conservation, they have to be moving together in the direction of the original motion of the ball. So in this case, in an inelastic collision, that first object that came in wasn't slowed down completely. It still carries with it some of its motion, and that's again a very common result for inelastic collisions. Now, the most extreme case of this, our perfectly inelastic collision, is if the two balls are then moving together at the same speed. We'll call that v prime. In this case, our equations change slightly. We've got the mass times the initial speed, and then 2 times the mass in the final speed because it's two objects of the same mass moving together. In this case, we only have got one unknown quantity, which is the final speed. So we actually don't even need the energy equation at all. We can solve for the final speed just using our momentum relationship. It's just 1/2 the initial speed. However, that energy term is actually useful because what it does is it allows us to figure out how much energy is lost in this interaction. So if I substitute our v prime back in to our kinetic energy equation, then we can solve for the final kinetic energy, and we find that it's about half of what our initial kinetic energy is. And as we'll talk later, this is the maximum amount of energy that can be lost in this particular system because it's a perfectly inelastic collision. Now, to round this off, we talked about superelastic collisions as also being a possibility. And again, all this does is just flip the sign for the inequality for the kinetic energy. In this case, the final kinetic energies added together are going to be greater than the initial kinetic energy because we've been able to extract energy from some part of the system to add into the kinetic energies. That's the definition of superelastic. So again, the math is completely identical. We end up with a similar inequality, but in this case, the only way for that to work is for the combination of 2 times the speeds multiplied together have to be less than 0. Now, how do we do that? Well, remember our quantities of velocity have direction, and even when we talk about one-dimensional motion, we can define one direction to be positive and one direction to be negative. So the only way for this to work out is if our final speeds are pointing in opposite directions. So without even knowing the details of the masses, the speeds of these objects, just looking at how these relationships between momentum and energy work together, we can say quite a lot about the resulting motion of a particular collision, at least in this one-dimensional case. Now, when we get to two-dimensional collisions, it gets a little more complicated because we now have to consider the momentum along two different directions, and we have to be very careful with our geometry. But in the end, it's very similar in the end. We're just going to write down our initial and final momentum and our initial and final kinetic energy, and then relate those together depending on whether it's elastic, inelastic, or superelastic. So for our general case here, again, where we have two objects with the same mass that then scatter out in different directions, we can write down our momentum along each axis, And so along the x-axis, which is across the page, we write down mv1 for our initial x momentum, and then we write down the components of the final momentum, keeping in mind that we have to add in our angle factors here. So I've labeled two angles with respect to horizontal axis, so that means that these momentum are multiplied by cosine theta, because that's the adjacent side for our momentum vector. And similarly for our y-axis, we've got no momentum at the start in the y direction, so that's 0, and our final state is going to be the sine factors. And notice I've actually made sure to put in a minus sign here because I'm assuming that perhaps one object is moving in one direction and the other is moving in the opposite direction. And that's going to be necessary in order to add up to 0 in the end. And we can also remember that these two terms are going to be equal because we've assumed that this collision is so short that there's no time for the external force to change the system momentum. Now we can also write down the kinetic energies, and it's going to depend on whether this is equal, less than, or greater than what kind of collision we have. But notice it's exactly the same relation. Because we only care about the speeds of the objects, it doesn't matter which directions they go. This is exactly the same equation. Now in this case, we've actually got 4 unknowns in our quantities, the 2 speeds and the 2 angles, and we've only got 3 equations. And this is very common the case for these two-dimensional collisions. We actually have an under-constrained problem. And so often you will find that there's another constraint that has to be made that, for example, we detect one of the particles moving off at a particular angle, or we measure the speeds in some way, and that gives them constraints on the other quantities. So just keep an eye out when we're looking at two-dimensional collisions that you're always going to need to have a 4th quantity or 4th equation or a 4th constraint in order to uniquely solve for the motion of our particles. The last kind of collision we'll talk about is not a collision between free particles, but a collision between an object and a fixed object, one that is in contact with the external environment in such a way that it won't move. Now, we could be flexible with this definition. We could allow that object to move around, but let's take the simple case where it's fixed because that's only just a shift in our velocity system that can allow that object to move. For example, if it's a moving wall or something like that. So let's take a fixed wall in this case, and let's send a ball at it with some initial speed. In that case, when we're talking about the collision, that ball can hit the wall and it can do a number of things. It can bounce backwards, it can stick there. In these cases, we're looking at different kinds of energy exchange in the collision. But let's look at the momentum of the system first. When we look at the initial momentum, that's just the mass of our object times its speed going in. When we look at the final momentum, in this case, if it's bouncing off, it's going to actually have some speed in the opposite direction. Now, this is a quantity that's positive and a quantity that's negative, which means there's no way that these quantities are equal to each other. But we'll see that in just a moment. If we write down the kinetic energies, we can write them down quite simply. And again, those momentum cannot be equal to each other because they're pointed in the opposite direction. Now, what does that mean? It means there's got to be a force acting on the ball as a result of this collision. And that force is going to be a force from the wall onto the ball or the object that's hitting it. And of course, there's an equal and opposite force acting on the wall. Now, these are internal forces. So how is it that I have a change in momentum if the internal forces don't matter? Well, if this wall is fixed, it means it's also attached to something. And so in the end, that internal force, or that force that's changing the direction of the ball, is really a result of the connection between the internal environment, the ball on the wall, and the external environment. And if this wall is fixed, it means that no matter how fast this interaction happens, it's still going to have an external force acting on it. So in these kind of cases, we may be interested in what the external force is, and that will depend on what kind of bounce that we're going to get off this ball. What kind of collision is, again, depends on the kinetic energy. We still have those same equations. So if we have an elastic equation, we set these equal to each other, and that immediately tells us that the speed coming off is exactly the speed coming in, because we have to have the same kinetic energies in both cases. We could have an inelastic collision in which the speed is less as it comes off. We can even have a perfectly inelastic collision where the ball just stops. That's when we throw a lump of clay at a wall. In that case, the speed at the end is 0, and we can calculate the energy loss from that as well. That's just equal to the kinetic energy coming in. And we can also have a superelastic collision if we have some kind of interaction that happens at the surface that adds energy to the system. That's going to give us a greater speed. In each of these cases, we have to take into account that there is an external force that's acting on the system because it's not a completely closed system. That wall is connected to something on the outside. But in any case, we can still write down these equations and solve for the unknowns. And look at how these knowns depend on the type of collision that's actually occurring. So in summary, we have different ways of looking at collisions. If we have a free particle collision where you have two objects that are interacting with each other without any external forces acting, or over short enough time those external forces don't matter, then we can immediately assume that the exchange doesn't change the total momentum of the system, and we can use momentum conservation as one of the ways of solving for our unknowns. We can also look at how this collision depends on the energy exchange then, and we can break that down into elastic, an inelastic, or a superelastic collision, and that will determine whether the kinetic energy is constant, decreases, or increases as a result of that collision. By setting these momentum and energy equations to each other, we can solve for the unknown factors in here, which might be the speeds or the angles at which these particles take off. And of course, when we talk about angles, that means we have to take into account momentum along multiple axes. And then finally, if we are actually doing collisions with fixed objects, in that case, we can't make the assumption that there's no impulse, because that external system is intimately connected with the parts of the system we're interested in. So in that case, we might actually want to calculate what is the force that's coming in to make sure that the object that's maybe moving or colliding changes its momentum as a result of the interaction. So we may be interested in the force of the interaction, or we might be interested in the timescale over which that interaction occurs. In either case, we're going back to our momentum-impulse relationship.